All right, so one thing I forgot to mention with existential quantifiers, we also see this symbol sometimes. We see an exists symbol with an exclamation mark. That means there exists uniquely. So if we say there exists exclamation mark X, that means there exists a unique X. So it means there's exactly one X for which a statement is true. So exists with an exclamation mark means there exists uniquely. So exist means there's at least one. There could be more than one. Exist exclamation mark, there's exactly one. And we can also do things like put a bar through this to say there does not exist. All right, I'll probably give you some homeworks Friday that deal with existential and universal quantifiers. So let's talk some number theory. Number theory can be an awesome subject to study and work with because numbers are relatively simple things. We're usually talking about integers. We're usually talking about natural numbers, often positive natural numbers. So, 1, 2, 3, 4, 5. Numbers are simple things. We learn about them when we're a kid. If we don't know any mathematics, we still know how to count the number of trees that we see, right? So it's the theory related to these basic numbers. And because of that beginning, a lot of what number theory deals with is very easy to understand. A lot of the questions that number theory asks are very easy to state in a way that anybody can understand them. But a surprisingly large number of these questions are extremely difficult to answer. And answering them in some cases takes hundreds of years. In some cases the answers are still unknown. So it's a really wonderful area that attracts a lot of amateur mathematicians, people who have perhaps no or very little training in mathematics, but still can understand these fundamental problems and can try to tackle them. And this was how I got into mathematics as a kid, and it's ultimately how I got into computer science, was through some number theoretic questions. So it's a fun field to work in, and it leads to some surprising results. It leads to things like coding theory. It leads to things like, anytime you buy something at the store, there's a little barcode on it, right? And that barcode identifies the product with a series of light and dark bands. How you make a mapping from that to a list of products is number theoretic, and how you make it so that you can't just change one of the bands to turn the TV set into a bottle of hand sanitizer and buy a new TV for $2, right? And number theory leads us to things like cryptography, which has been used for thousands of years, but which we use pretty much on a daily basis now anytime we do commerce on the web. Right? Anytime you buy something with a credit card or send your password into Clark to log on to the network, or send it to the Linux server to log in, if you just typed in your password and the ASCII code for those got sent through the wireless system, everything would be insecure because anybody can listen to the wireless information coming in and out of a router. Right? So it has to be encrypted in some way to prevent that kind of eavesdropping from disclosing confidential information. But that's got to be done in a way so that you don't have to set up a secret password with the server every time that you want to send information to it. Right? Like when you're a kid, you have your decoder ring, you say, okay, the password today is 17. And now you can send your friend a message, and they know how to decode it because they know the secret password is 17, and they can send you messages. We don't want to do that every time that we send an order to Amazon or we try to log into the Linux server. So there's got to be a different way to do cryptography. It's something called a public key system or an asymmetric cipher, and that all comes out of number theory. We'll actually learn enough number theory to learn at least the algorithm for something called RSA. It's a public key crypto system. that almost broke the government at one point, perhaps. So we'll go into a lot of cool stuff with this. Most of the number theory we're going to talk about boils down to one concept, which is divisibility. So let's keep thinking about integers throughout all of this. I don't think we'll ever talk about reals in here. Divisibility. So we know we can divide numbers. We're smart. We can say 2 divided by 3 equals 0.66667 if we round it off. Right? But this is not an integer, right? So if we're only allowed to work about integers, 2 divided by 3 is undefined. So the division operation for integers doesn't always make sense. Now if I try to do 6 divided by 3, yeah, that's just 2. That works great. 5 divided by 3 doesn't work. So we introduced this concept of divisibility to ask, is one number divisible by another? So here's a definition. And we're going to have a fair number of definitions up front. An integer, but I'm going to put that in parentheses because we're just going to deal with integers. So an integer m is divisible by x if, well, one way to think about this is m divided by x is an integer. But I'm saying division doesn't really work if these things aren't integers. So let's find a better way to say this. M is divisible by x if there exists some quotient q contained in the integers such that m equals x times q. So m is divisible by x if there exists a q such that m equals x times q. So is 6 divisible by 3? We can ask, does there exist a q in the integer such that 6 equals 3 times q? So is there an integer such that 3 times that integer equals 6? Yes. We can have q equal 2. So 6 is divisible by 3. Is 5 divisible by 3? Does there exist a q such that 5 equals 3 times q? And it's pretty easy to convince yourself no, because if q is 1, you only get 3. If q is 2, you get 6. If it's bigger than 2, it's more than 6, so it can't be 5. If it's less than 1, it's smaller than 5. So there is no such q. So 5 is not divisible by 3. 6 is divisible by 3. Is 0 divisible by 7? How many people say yes? All right, so what's the q such that 0 equals 7 times q? Q equals 0. So yes. In fact, 0 is divisible by pretty much every number. I guess technically 0 is divisible by 0 if we do this, because it's equal to 0 times 0. Don't tell your math teachers, though. Is 2 divisible by -1? Yeah, it's just -1 times -2. So yeah, that's divisible by -1. Mostly we'll stick with positives. But if someone asks you, yeah, those are technically divisible. Okay, so the following are equivalent. M is divisible by X. We can also say X divides M. We can also say X is a factor of M. We can also say M is a multiple of X. So just different ways of saying the same thing. M is divisible by X, X divides M, X is a factor of M is a multiple of X. We can write this in a shorthand as follows. We can write X a vertical bar in M. So this thing means X divides M. So we think of this little pipe as meaning divides. Okay, this is not X over M, X slash M, X backslash M. Those are all different things. Okay, this is X vertical pipe M means X goes into M, X divides M. And it's a bit of unfortunate notation because it kind of looks a little bit like X slash M, but it's really not. Right? It's really talking actually about M divided by X. So if you kind of slip to that, you're actually flipping things around too. But we'll use this a lot because it's easier than writing divides. And so one more piece of notation. If we write that vertical bar with a slash through it, this means X does not divide M. And that's all we need to do a lot of fun stuff. Another way to think about this is if we were to take M and divide it by X, even though they're integers and X may not go into M evenly, right? If we take M and we divide it by X, we can write it as some quotient with some remainder, right? So 17 divided by 3 is 5 with a remainder of 2. Okay, saying M is divisible by X means if you do M divided by X in that way, your remainder is 0. And that notion of divisibility is going to be a launching point for a whole branch of mathematics we'll brush lightly, which is called modular arithmetic. And that's where all the good stuff like RSA and everything comes from. So we'll come back to this notion of a remainder being 0, meaning that something's divisible. All right, well, we're back to proofs already. We can do proofs of some simple properties of divisibility. So here's a theorem. If A divides B and A divides C, then A divides B plus C. So for example, 3 divides 12, and 3 divides 30, so 3 divides 42. Or if we put this in more common speak, the sum of two things that are divisible by 3 is also divisible by 3. And that shouldn't be too startling if we step back and we really think about it. This statement here, 3 divides 12, says 12 is equal to 3 times something. So I don't know, maybe 12 equals 3 times some integer x. And this statement, the 3 divides 30, says 30 equals 3 times some other number. Well, if we add 12 and 30, 42 is 12 plus 30. That's just 3x plus 3y, which is 3 times x plus y. Well, this is an integer, so 3 must divide 42. And so from that insight, we could actually make a bit of a formal proof. So let's start off by saying a divides b. That's given. So statement 2, we can say there exists an x such that b equals a times x, where x is an integer. And that's the definition of divisibility. And we're also told that a divides c, that's another given. And we can apply the definition of divisibility, but I'm not going to say there exists an x such that c equals a times x, because I've already sort of given x a value up here in statement 2. X is the value in z such that b equals a times x. So I'm going to write this as there exists a y in z such that c equals a times y. And that's the definition of pipe. Divides is divisible by. And now I'm going to write down the following statement: b plus c equals ax plus ay. And that's substitution of statements 2 and 4 into this left side, b plus c. There's no b plus c up here, but that's okay. I'm not saying that there is. I'm saying if I write b plus c, that's going to be equal to ax plus ay, where x is the thing that satisfied this and y is the thing that satisfied that. B plus c equals a times x plus y, that's just algebra. But now if I look at my definition of divisibility again, since b plus c equals a times some integer, I can state a divides b plus c, and that's the definition of divisibility. Right? Because I found a particular integer, namely x plus y, such that b plus c equals a times that. And that's what we wanted to show. And it turns out we can prove all kinds of properties of this divides operator using a very similar approach. And I'll probably give some of these to you on a homework Friday also. But similar things we can show. If a divides b, then a divides b times any integer. If a divides b, then a also divides 2b and 5b and negative 17b, and so on and so forth. If a divides b and b divides c, then a divides c. So we've got a bit of a transitive property to divides. And we can put all of this together and sort of come up with the grand Uber theorem of all of these. If a divides b and a divides c, then a divides m times b plus n times c for all m and n in the integers. So if you're in 215, if A divides B and A divides C, A divides all linear combinations of B and C. And we can prove each of these exactly the same way. Take the definition of divisibility, use that to write B as A times X, C as A times Y, and then plug those versions of B and C into MB plus NC, and you'll be able to factor out an A. And so you'll see that A divides that linear combination. All right, questions so far, other than why? Okay, let me give you the grand theorem of all of this. And this is called the division algorithm. But it's not an algorithm, it's just a theorem. And I used to present this very formally, and it's just filled with backwards e's and conjunctions and disjunctions, and it leaves the reader kind of wondering what it's all about. So let me give this to you in sort of a plain spoken kind of way, and this is the way we'll use it, and then we can formalize it later. So let's just think about positive integers for a moment. Okay, so let P and Q be positive integers. We can write P equals something times Q plus a remainder, where X and R are integers. In other words, we can write P as some multiple of Q plus a little bit left over. Okay, so for example, P equals 17, Q equals 3. We can write 17 equals 5 times 3 plus a little bit left over. Okay, 5 is the number of times 3 goes in, and 2 is the remainder. And we know how to do this, right? This is how we first learn to divide things before we learn long division. It goes in a certain number of times. Now when we do this, there's an unspoken statement, right? I could also have written 17 equals 4 times 3 plus 5. But I would have lost points from Mrs. Smith if I turned that in on my math paper in whatever grade that was, right? We could also have written 17 equals 0 times 3 plus 17. Well, that's correct, right? But that's clearly missing the idea of division. We could be really crazy and say 17 equals 6 times 3 plus negative 1. And that's also correct. I'd probably get sent to the principal's office, because then you're just being smart. So something about this one says this is the correct way to do this. Right, when we're looking for the remainder that we're left with after we do division, we really want a remainder of 2, not 5 or 17 or negative 1, even though technically we can put all of those in this form, right? So we can write P equals X times Q plus R, where R has got to be non-negative. It's got to be bigger than or equal to 0, and it's got to be less than Q. So it's something between 0 and Q exclusive of Q. So take two integers, keep them positive for now. If you take one and you divide it by the other, you can find it goes in a certain integer number of times with a little bit left over, such that that little bit left over is smaller than the thing that you're dividing by. And there's very little thought involved in doing this. So 37 divided by 5. Right, well, how many times does 5 go into 37? It goes in 7 times with a remainder of 2. 37 divided by 4, how many times does 4 go into 37? 9 times. And what's the remainder? 1. Right, 9 times 4 is 36. 37 divided by 6 is 6 with a remainder of 1. You got it? Alright, goes in 5 times with a remainder of 2. How about 10? Last one. Yeah, 3 times with a remainder of 7. 10s are nice because if I do what's the remainder going to be? It's going to be, you know, we're going to get some big, long, horrible thing with a remainder of 3. So doing this division by 10 is really nice. Okay, so we're going to want to keep this in mind, and when we talk about finding the remainder when you divide one thing by another, we're looking for that number, right? Not 37 is equal to 1 times 5 plus 32, right, which it is. We're looking for the remainder, in this case between 0 and 4, in this case between 0 and 3, in this case between 0 and 9. Now, like I say, stating that formally gets kind of complex, but this is the essence of the division algorithm. This theorem says that there is always a unique remainder like this when we divide. And, you know, sometimes it could be 36 divided by 6 equals 6 with a remainder of 0. Sometimes that remainder is 0. That's okay. But we can always write this as, you know, something with a remainder between 0 and the thing we're dividing by minus 1. Where is this going? It's going to turn out that if we just think about remainders, we can do a lot of arithmetic on very large numbers by just doing arithmetic on the remainders when we divide by something. So if we divide numbers by 10 and we just look at their remainders, we can very easily tell what the last digit is when you multiply two numbers together. How? Take the last digit, multiply them, see what the last digit of that is. So if I take this number here and I multiply by this, whatever I get is going to end with the last digit of 3 times 2, which is 6. If I multiply by 8, whatever I get is going to end with the last digit of 3 times 8, 24. It's going to end with a 4. And we're going to find lots of things that we can do. We're trying to do something on very large numbers, but instead we work on what we call their modular equivalences, the remainders when we divide by something. And the bulk of what we do in this chapter is going to be working with very simple small numbers because they're just remainders, but learning to extrapolate from that information about the original numbers, which are very big and cumbersome. And that's how things like RSA works. We work with these 100-digit numbers, but we can do things with them. We can multiply them and add them and answer questions about them because we're just going to look at their remainders when we divide by certain things. All right, so that's where we're going to go on Friday and into next week, is playing around with these concepts. So we'll formalize some of this and we'll go from there. All right, have a good day. I will see you next time.